هل الصورة تطلع عندكم واضحة؟ يعني بالصوت رجاء لأن أنا ما قاعد أشوف الشات.
واضح دكتور.
واضحة.
ايه لما طيب تمام.
تمام، أحسن من البلاك بورد.
100%.
أكيد دكتور.
أوكي زين، نسمع صوتكم. عموما I will switch يعني في كل المحاضرات القادمة الحين to Teams. يعني it requires for me يعني I don't know because sometimes I need to download it from here, then I have to upload it to the Blackboard. But currently you will have all the lectures online on the Teams, okay? Available on Teams. In this chapter, I will cover the current transformers and the voltage transformers. And as I mentioned in the introduction chapter, these two are the through which the relays, protective relays, which is the most important component in a protection system, requires an information. What's the level of the currents? What's the level of the voltage at that instant of time? And based on which it will take a decision. Now, the question: how do we choose? What are these? What the types of current transformers are there, and voltage transformers? How they are connected, and how we select them for the protection system. Is there a difference between a current transformer used for measurement purposes, or those used for protection principles or applications? How can we select transformer that will not saturate during the operation or during faults? No, saturation of these current transformer will lead to maloperation of protective relays for which the protection function will fail. And this is what we don't want to happen by selecting proper protection function. I'll just bring my this is the so what I'll cover in this chapter, the following. So what's the purpose of the CTMVTs? This generally I already mentioned in the previous lecture. Standard secondary ratings also I mentioned about it in the previous lecture. Symbols used for the CTs and VTs, and the polarity marking. Current transformers types and difference between relaying and metering characteristics, the voltage current characteristics, and the knee points, and the burden. So these are general definitions, okay, today. So what are the purpose of the CTs and VT and a protection system? Are basically, as I mentioned, they provide the main primary functions to reduce the current for current transformer and the voltage for the voltage transformers to a lower and a standardized level at the output of the current and voltage transformers. And this standardized level or output is, mostly suitable for protective relays. And as a result, the size and cost of relays would reduce because and why it's standardized? Because if it's not standardized, so each manufacturer will produce or will manufacture a CT that has different output. And also, as a result, the relay has also to cope with this relay designs. However, if it is either 5 or 1 for current transformers, this is the expected output. I can design a relay that is expected to handle this level of currents, okay? So standardization makes also the spare part that you have to keep in your systems, and the cost of manufacturing is less, and so forth. The second purpose of current and voltage transfer to provide galvanic isolation. And we say galvanic isolation means the high voltage system is isolated from the low voltage system, which represents the relay side, by using magnetic isolation. You know, transformer has primary and secondary, and these two windings are magnetically isolated, okay, by the core. So isolate the relay from the high voltage systems. This is the second purpose, and their output, okay, as I said, there are standards. Permits the use of standardized current and voltage. The outputs of the CTs and VT are at standard voltage and current levels, so that we can use the same relay, okay, can be used at any point in the power network. What are the ratings of the output of these CTs and VTs? Normally, the standard CT output or secondary rated current of the CT is either 1 ampere or 5 ampere. And there are some manufacturer, I'll show you later, in the relay, they will design their relay to accept either 5 or 1. Okay, whether you will use it in normally Europe, like in Bahrain also, will use 1 ampere, and in North America they use 5 ampere. But relay manufacturer now, they started to provide either 5. The consumer can select 5 or 1, depending on the main CT output. The voltage transfer normally is between 110, it's not 150, 110 to 120. It depends also either the IEC or the European standards or the North American standards. And this voltage, the voltage is line-to-line voltage between two phases. It's 120 is the output of the main voltage transformer, while the primary could be 400 kV, it could be 11 kV, it could be the actual voltage of the circuit. The symbols for CT is either this, but we can use also this symbol, okay, which is a circle with so this is the primary. This is now represent the primary. This part represent the primary, okay, which is just one turn. Okay, the cable passes through the core. Okay, and the secondary is wound type. So this is the secondary. Okay, and so this is the secondary output. This is the secondary, and this is the core. Iron core. All right. So this is primitively a transformer. This is current transformer, same as other transformers, except the primary is not a multiple turns here. It's just single turn mostly. But we have some CT where we have more primary turns. Okay. The secondary can be either one or several. Have some tabs here, so that you can have multiple ratio. Okay. So we have multi-ratio CT, where the output secondary winding has different tabs to pick the ratio. These dots represent the polarity. يعني, how's the if you inject a current at the primary in this direction, how the secondary current? So the polarity of this current into, so this is not what I am showing is not right now. A current now, in this case, current here will leave the dot here. The primary has to be inside like this. entering a dot. So a current entering a dot at the primary side correspond to current leaving a dot at the secondary side. Okay, so what does that mean? If I inject a waveform like this at the primary cell, so this is I1, the secondary one will be, the secondary will be in phase. If you correspond, the secondary will be also in phase like this at a lower current, of course. This is I2 in terms of polarity. Okay, this current will be in this direction in this case. Okay, so this current polarity is same as this current polarity. And this is very important. So why we are interested to know the direction of the currents? Because as I mentioned earlier, if we are using a protection that requires direction of currents in the principle of the protection, then it's very important. Like in differential, you need to compare two currents. If the direction is not correctly matched, we would have a maloperation because of the incorrect connection. All right, suppose we have directional relays. Also, we need to know the direction of the CT connection. CT polarity is very important. Similarly, for a voltage transformer, we can have the voltage transformer symbol as like this. The two overlap circles. Or we can make it as two windings. Yeah. So the two windings like this one now. This is like a voltage transformer where this is the input from the voltage, and this is could go to the neutral, or so this is the voltage of one phase now, and the output comes from this box. Okay, the second, which is these two coming from here, and the primary is this. You say this is the primary side, V1. Okay, and this is the bushing, it's insulators. The polarity marking in the same way, right? If you apply a voltage plus minus, polarity at that plus minus for AC is just at specific moment of time. The secondary will be the polarity of, if you have the polarity marking, dot marking is here with respect to this, means if this is plus at that instant of time, this will be also plus with respect to this at that instant of time. So it is the same way, the polarity is like this for the primary V1, and V2 will be in phase in this case if you connected in this polarity. Okay, this is V2, they are in phase. However, if I reverse polarity, if I take both here instead, the output will be inversely. It will be like this. Okay. Of course, the secondary at lower voltage than the primary. So they will become out of phase. So it's also very important to know the polarities of the. Okay. In testing relays, one of the things we have to test is the polarity, is the connections. Okay. Is the connections is correct for these CTs to the relay or not? In high voltage system, you know, the CTs, these ZTs and VTs doesn't look like a regular one that you might see in a lab. They are huge, okay? And if you look to this picture, This is a CT. Okay. This is a CT, and that's a VT. And now, where is the primary and secondary? See, the primary is this. So the cable comes in, okay, it goes down to the winding, to the core, and goes up and continues. So this is the primary, okay? And the secondary, it's a core here. I'll show later. So the secondary is a core. This is the core. The secondary is here, and they take the output here. So this is the red one is the core, iron core, which is this part. Now, while the VT it has one terminal, as you can identify by showing here. This is in and out from another place, where they are joined at the same location for VT. This is same point, and if we take from here, so the this is as you go down. So we have here the transformers. We have the transformer and the secondary primary and the secondary. They are taking output from this box, terminal box, and this is the terminal box of the CT from the secondary side. And this is the second terminal, which is considered as a neutral point. So this is one phase, and this is also one phase. As you can see, there's for phase B, and the last one here for phase C, and similarly. And in terms of connection, we can connect CTs normally. Suppose for a transformer protection, for example, we need a current to measure at the primary side and current at the secondary side, and we compare them. And this is called current differential principle, current differential principle. So a CT, is the voice is okay, still okay?
Yes, doctor, it's okay.
Hey, doctor.
Okay, so the current transformer here, this is one current transformer. I'll just show it with. So this is a current. Afwan. Okay, so this is a current transformers. Normally H, and these.
I hear you.
Doctor, you have been muted.
Is it okay now?
Yes, we can hear you now.
Yes, doctor.
Yes.
Where did you? Are you watching this? Okay, or is this slide is okay? Fine with you? Yeah,
For me, could you repeat the VT word, please?
this one?
The VT, yeah. No. The slide, the identifying the CT from VT. The previous one.
This one?
Yeah.
Yeah.
Yes.
So I just was drawing how do you identify? This is at high voltage systems, where the current, how to identify it? Normally, CT has two terminals at the top. So if you imagine like we have one winding for the primary and another winding is secondary, and we have a core, right? So the primary comes here. Comes through this terminals, comes down to the core. This is the red circle is the core. So throw it and goes out. So this is the primary. The secondary is wound at the core here and goes to the box here. We call it the terminal box. يعني البوكس من خلاله نحصل أطراف السكندري winding. While the voltage transformer has only one point at the top to connect the cable to. Okay, here it has N out, here it has just one N. So this terminal for the voltage transformer, they take here. This is the primer still. The primary winding is here. And the secondary winding is here. So this is the terminal box from which we take the secondary winding output. The second terminal of the primary winding is taken as a common point for the three phases, the neutral point. All right. As you can see, this is the second voltage transformer. The third, for each phase you have one. And these three phases will be connected at the end as a star. Okay. And these are for the CTs. Now, for how do we utilize this current and voltage transformers in real systems? We can connect, let's say, for a transformer protection. I need, for example, I can use the voltage CTs and VT for either measurements, or we can use it for protection applications, and both, for example. But normally, generally the CTs used for protection is not the same as the one we used it for measurements. I'll show you later why. But nowadays we can have a CT that is applicable to both of them for both applications. So for the primary side of the transformer, I want to measure the primary current that goes to the primary winding of the main transformer. This is the power transformer. Okay, it's not the CT what we are talking about. Our CTs are instrument transformers. Their use is not to transfer power from one side to another. It's their purpose to either measure the quantities or monitor that quantity for protection application. So here, this is the primary winding, is abbreviated as H. The secondary winding as X. Normally, American standard, they use H for the high current, for current transformers, and X for the low current side. And for voltage transformer, H represents the high voltage side, X represents the low voltage side. So in this case, I will put the primary in the this is the primary winding, the secondary winding. Similarly, at the secondary side of the power transformer, I use this is the primary side, the secondary side. Then I can compare these two, the current from the secondary side of the current transformer. I can put an ammeter to measure this current. This could be maybe, let's say, 500 ampere. Okay, while this can be 5 ampere. Okay, the secondary side. So, but here 5 ampere represent the 500 ampere. So I have a ratio of 100 from this, let's say 500 to 5 ratio in this case. I can use this current also to compare a relay that compare the current at the primary or the current at the secondary, and we call it, this is like a current relay, and this type of relay is termed differential relay. Okay, so this is a differential. And we have one chapter on this. Differential. Okay. Relay. And the second type of relay, there's some other relays. I can take the voltage output from the VT I can measure that voltage. So a voltmeter can measure the primary side voltage. Primary side could be, let's say, 11 kV, while the secondary here I can use a voltmeter that has a range of, let's say, 600 volt or 400 volt range. As I mentioned, the voltage here, rated voltage is 120 line to line. Now, this is a phase voltage, even less. So I can use a voltmeter to measure the primary voltage. And similarly, I can use this voltage to a relay, which compare the current from the current transformer with the voltage, this voltage. And this type of relay that require voltage and current normally, like directional relays. They call it directional relays or impedance relay, directional. Okay, there are so many relays that require a voltage and current to for the protection applications. We have also wattmeters. Wattmeters require the current and the voltage, so that I measure the power flow, active and reactive power to at the primary side of the transformers. I have relays that requires only current. Okay, so relay that needs only current. So this current that goes here, it goes to the primary, to the relay of this relay current winding, this relay current winding, okay, and goes to this relay also that require only current, okay. And one of the examples of this is like an overcurrent relays, okay. An example is overcurrent, over OC, overcurrent relays. I'll have one full chapter on overcurrent relay. Don't worry about this, okay? So I have chapter here, chapter on this, chapter on that, okay? So we'll go on details. And for the, so this is like connections where I can use the VTs and CTs for measurements, like ammeter and voltmeter, or protection. Similarly, here I have relays that require only voltage to operate, voltage operated relays. One example is under voltage and over voltage relays, okay? U under voltage, UV, under voltage or over voltage relays. So for this relay to know this is low voltage or this is high voltage, okay, higher than the rated, it just monitor the voltage here, and based on what it takes, that is this is a low voltage or this is high voltage at that moment. Now I'll start with the current transformers first, then inshallah in the next part I will cover the voltage transformer. Types, there are different types of current transformers. One of them is wound type. Wound type, normally the primary side and the secondary side formed with using a winding, okay? So in this case, in this figure shows only the secondary winding, which is X1, X2, but the primary winding also, sorry, this is not a wound type, this is the wound type. This is a window type. A window is like an opening, opening through which you can pass the primary cable through, okay? So the primary here represent the cable that you will pass through, like in the figure I showed you. And the figure, let me check. Yeah, here and as you can see, this cable goes in through a window, through the CT window opening. So this is represent your primary, the cable passing over primary. This is the phase 1, this is phase 2, phase 3, and this is say the neutral. Okay, And the secondary is taken from here. This is the secondary output of the CT. So this is called a window type, okay? Or so window type, it has only a secondary wound on a core. This is the core, okay? And this is the secondary. So this is the polarity marking, dot marking. And this is the terminal of the output, secondary, X1 and X2. This is a window type. A bar type is like the primary is it has a bar, okay, which is like this bar. This is the bar, which is already connected. Instead of passing the cable through the window, okay, here no, you just connect the primary here cable. Okay, the cable comes in, and you with a nut and bolt you connect also the cable leaving here. Okay, and this is the case if you have the cable size. If you have a cable size is big enough that doesn't go through the window opening, okay, then you use this types of CTs. We call it bar type. The thickness of the cable doesn't go through the window. And this is the representation of the bar, which is represent the primary. And this is the core. And that's the winding wound on the core. And we have also wound type. Wound type, you have both the primary and the secondary wound on the core. Here it doesn't show you the primary, but also have another winding wound in the same core, and you have we call this wound type. And the third one, fourth one is the bushing type. A bushing type is the CT which are connected directly at the bushing. Bushing is the insulator. Like if you have this is now the CT. Okay, this is the CT, bushing CT, which is in, for example, a transformer or at the circuit breaker side, at the terminal of a circuit breaker. I don't know if I have a picture here. This is a CT. In the previous chapter, I had a picture for a circuit breaker. So at the insulator board, at the output side of the circuit breaker, you can house or connect a CT. Okay. At the bushing. Bushing is the insulation part. This is, for example, this is a bushing, I say. Okay. But for a big transformer, large transformer or circuit breaker, they have also bushing. So it's connected somewhere here. I'm just representing this as a big transformer or a big circuit breaker. And this is like, we call it a donut type. If somebody likes donuts, this is a donut CT. Okay. This is like a window type also. This is another way of calling window type. This is a donut, same as in this picture, they use a donut type. Here the cable comes in, the primary cables comes in and leaves this side. And the secondary winding wound on the core, which is yellow here. And this is the terminals of the secondary. We have CTs can be also classified based on the number of ratio we can get out of that CT. We have single ratio CTs, we have dual ratio CTs, we have multi-ratios CTs. So for example, this CT, I can have the primary, this is the primary winding. Primary is just you pass a cable through this core, through this window, okay? And the secondary, you take it from here. The secondary here, you have two ratio. I can take between X1 and X2 or between X1 and X3. So if you take from X1 and X2, okay, you get a ratio of, sorry, from the X2 and X3, you will get a ratio of 400 400 to 5, you will get from x1 to x3. If you take the output from here, I'll get a ratio 400 ampere to 5 ampere. But if you take the output from x3 and x2, you get a ratio of 200 to 5. So it has two ratios. Similarly, this CTs has a multi-ratio. Depending where you take the output, if you take it from x1, from x2 and x3, from here, I'll take the ratio of this multi-ratio of 600 to 5. You can take 50 to 5 or 100 to 5. 55, you take the output from here. Or if you want to the output 600 to 5, you take the output from x1 and x5, as you can see. All right, so this is a multi-ratio CT. For high voltage system, the CTs are constructed not as simple as this, okay? For high voltage system, we'll have a CTs as I showed you in the pictures, something like this. And in this way, it has a primary winding, inside here. This is the primary winding, the yellow, okay? And these are the core at the bottom here. You have the core on which I have the secondary winding wound on this core, okay? And the output taken of the secondary side through this terminal box. These are the primary and core are housed inside insulated housing. This is a made of porcelain as an insulator, and sometimes it's filled with oil to provide further insulation between the conductors and the housing. Okay. So this is one type of construction, but we have other types like optical CTs, where we don't have a core here. And what's the problem with these types? If the core gets saturated, the output waveform will get distorted. The secondary current will get distorted with harmonics, and also its magnitude will get reduced if the core gets saturated. So there will be an error between ratio error between primary and secondary. However, in optical CTs, it doesn't have a core that saturates. So this is like a latest technology in CTs, and this is also based on Faraday's law, where the current entering here will make a magnetic field, and this magnetic field will interact with a light beam. So I have a light beam sent through a fiber optic, and this light beam will get deflected by the magnetic field strength. So the deflection will be greater if you have stronger magnetic field, okay? So based on the deflection between the light beam which was sent with respect to the light being received, the phase displacement is an indication of the magnetic field. There is no magnetic field, there will be no phase displacement, okay, between the sent light and the received light. And with this, there will be no problem of saturation here. However, this type of CTs has high accuracy, it has linear characteristics, okay? So it's like immune to core saturation. There will be no iron core, reduced size and weight of the CTs as compared to the oil or SF6 type. SF6 as a type of gas. There will be no oil, so it is safer from leaks if they happens. Can be used for relaying and metering. So you can use this current to provide current an emitter, or you can use it to bias a relay. However, it has disadvantages here. It requires a power supply for this light beam to get generated. it has a lower output. The output signal here, a light signal, it has to be amplified, and so the output here is low output that requires also amplifications. So what's the difference between relaying? When I say relaying means CT is used for protection purposes, and metering, CT is used for measurements purposes. Okay, and CT should be. What's the purpose of a CT? Generally, I want to produce a secondary output, which is faithfully represent the primary current. It shouldn't alter its shape. If it is a sinusoidal, the output has to be sinusoidal. It shouldn't alter its phase. Okay, so its phase and magnitude has to be preserved. So this is we call, and the secondary signal has to be faithfully represent the primary signal. There should not be. Only you change the magnitude ratio. Shouldn't change its phase. And so relaying CT means that for relaying CT or for protection, used for protection applications, normally it should handle current accurately up to, let's say, 20 times its full load current as rated current. So it should work accurately during that during fault. And in metering, however, it might have larger error during normal or under light load condition. But the purpose of protection to operate during full, during short circuit, and okay, it's not during normal operating conditions. So if there is a large error during normal operation, this is not an issue for the protection CTs. A high quality CT is thus required for relaying applications as compared to metering application. For metering, the meters normally, we measure normally full load, we don't measure faults conditions. So that's why a current transformer used for metering application should be rated up to 120% of the full load current. I don't want to, measure short circuit currents. Okay. However, if you exceed this 120% or higher than full load current, CT will get saturated in this case. So to show you the difference. Now, if we have the BH characteristic, this is same as because this is a core type transformers. The core has a BH characteristic. Normally for metering CT, have BH characteristic. The core size is small, so the magnetizing characteristic is linear up to this point, then get non-linear afterward. For protection CT, it has a longer linear part and it's saturated at higher flux, okay, as compared to measurement CT. In terms of its output, if I compare the ratio between the secondary and the primary current, the ratio has to be linear, right? Because if I have a CT that changed the ratio from 100 to 5, if I put a primary current 100, I should expect a 5 ampere at the secondary. If I put 1 at the primary, I should get 0.05 at the secondary. The ratio has to be same. Okay. Now, the ratio for a measurement CT up to the full load, if you primary up to full load, it's linear. If you exceed 120% of it depends on the manufacturer, they specify it for you. But if you exceed the full load with the percentage, the primary current to the secondary will not be constant anymore. The ratio will get reduced, okay, reduced. And if it's fully saturated at short circuit, the output is 0, although you have high current. If you go to like 20 times the full load current, this value, you have primary current, but the output primary current because the core is totally saturated. If you look to the waveform of the current at this value from the output of a metering CT, you'll see it like distorted. It's not a sine wave. However, for a protection CT, even if you put if you select it properly, even if you apply 20 times its full load currents, the relationship is linear. Okay, ratio is fixed, and the output is sinusoidal. Okay, if the input is sinusoidal. This is the typical excitation curve, which shows the secondary. This represents the secondary voltage in RMS here versus the secondary RMS excitation current, IE. So this is secondary excitation voltage, exciting voltage, and this is the exciting current. So what is exciting voltage and exciting current is, if you have a CT and CT, this is the primary and this is the secondary. Okay. So if you inject a current here, okay, and I would now the model of the secondary, let's see. Yeah, this is an equivalent circuit of a secondary side of a CT of a current transformer. The excitation current is the magnetizing current that goes in the magnetizing branch. Okay, this is IA, and the excitation voltage is the voltage at the secondary side of the current transformer, which is Vs. So if this curve plots the relationship between Vs and IE. Okay. So this is IE versus Vs, V excitation. All right. So now this is a multi-ratio CT. It shows us now the characteristic. If you choose 600 to 5 ratio curve, this is the curve. It's linear up to this point, and this is called the knee points. The point at which the curve changed from linear to a non-linear, okay, curve, the knee point, or the point. And now this point, where is the point? It should be here or there. How do you find the knee point? The knee points, by definition, okay, we have two definitions for it, and similarly the knee point for the other CT ratio, 500 to 5 ratio curve, which is this is the knee point, and this is the knee point for the other ratio for 50 to 5 and so on. This is a multi-ratio CT. A knee point is defined as by IEEE, or the American National Standard Institute, ANSI. They defined the knee point is the point at which the straight line curve of 45 degree is tangent to the magnetizing characteristics, or to the curve. So if you take this straight line, blue line, tangent to 45 degree and touch this characteristic at this point, so this is the knee point. So this is called the knee point voltage, okay? And this is the current at which the excitation current at that knee point correspond to the knee point. For IEC, which is the European now standard, unified standard, IEC, they define the knee point as the intersection between, if you take a straight line tangent to the linear part of the CT, this is the linear part of the characteristic. If you take a tangent line here and a tangent line to the linear part at the saturation area, this is the linear, and you intersect these two at this point. This is the knee point correspond to IEEE definition, and this is the knee point voltage, and this is the current, all right, at which that knee point is defined. So generally, the error will be excessive, the CT error will be excessive if you exceed the knee points. So we should design our CT such that we don't go beyond the knee points, okay? To maintain the error small, okay? We have also burden definition. What's a burden? Anything that's connected at the secondary of the CT. This is the secondary of the CT. So the load which is connected to the secondary CT, we call it a burden. Now burden consists of two items. The lead يعني الوايرات اللي استخدمناها في توصيل CT secondary to the relay or to the meter. So ZR here represent the resistance or the impedance of the relay or the emitter, and ZL here or RL represent the resistance or impedance of the conductor that we have used to connect the secondary to the relay or to the meter. So this burden represents the sum of the two, okay, and we abbreviate it with ZB, okay, and so either this the burden is measured in ohm or given in ohm as a unit or given in volt ampere. If you multiply this impedance ZB by the rated secondary current squared, I secondary, and this is of course the current in the solid line is I primary. Okay, so if you take the secondary current, what is the secondary rated? When I say rated, is either 5 or 1. This is for European standards and this is for American standards. So I can convert this from ohm to volt ampere by multiplying by the rated secondary current of the CT. Burden, standard burden for this table shows you the for metering application, and this standards for IEEE standard. The burdens are given as B 0.1 means 0.1 ohm. The impedance, the burden is a maximum of 0.1 ohm. And for B 1.8 is the impedance maximum is 1.8 ohm that you connect at that secondary side of the CT. And if in terms of the volt ampere, you can convert this in ohm to volt ampere by multiplying. This is IEEE normally secondary is American standard. They have 5 ampere secondary. So if you take 25 square I secondary rated square times the resistance burden, you convert to S burden in volt ampere. So what's the secondary is 5 ampere, which is 25, 5 square, 25 times 0.1 ohm, 25 point times 1, 2.5 volt ampere. Okay, so this is in volt ampere. And this is an ohm. And 1 point class, this is the burden class of 1.8, so it will be 45 volt ampere if you multiply 1.8. Similarly, for relaying applications, the burden either 1 or 2 ohm or 4 ohm or 8 ohm. These are the 4 standard burdens. And so it's 1 ohm, it's mean 1 ohm times 25 to 25 volt ampere up to 200 volt ampere for 8 ohm burden. Now in IEC, the burden are given in not in ohm, it's given in volt ampere directly. So they have a standard burden of 2.55 volt ampere up to 30 volt ampere. For example, now if I have a CT rated 15 volt ampere, what is the burden in ohms for 1 ampere and 5 ampere secondary currents? So if we know that the Z burden is equal to S burden over IS squared. And I have the burden 15 over 1 ampere is the 1 ampere rated current. I get 15 ohm maximum burden correspond to 15 ampere. If this CT is 5 ampere rated secondary, this is the corresponding maximum burden that should be connected across the secondary. We should not exceed this burden 0.6 ohm, okay, in order not to exceed 15 volt ampere. So burden is very important. We select a CT such that we don't exceed its specified volt ampere or ohmic burden. This is another example. Suppose I have, I'll just check my time. Okay, still I have, okay. All right, so if I have this is another example. Suppose I have a CT. I want to select the suitable burden. I would like to buy a CT that it's suitable for my application. So calculate the volt ampere output requirement for a CT of 5 ampere, 5 ampere of course secondary. Given that a relay requirement at 5 ampere, means the burden of the relay is 10 volt ampere at 0.8 lagging power factor. So like I have a CT, this is the primary, this is the secondary, okay. And this secondary is now this I connected to, it has a lead resistance of 0.1 ohm. This is R of the lead, and it has a burden. This is Z of the relay. Z relay here is 10 volt ampere. The relay is 10 volt ampere, and the 0.8 lagging. So that's for the burden of the relay. So this is like X1 is the output of the CT secondary. So the ratio here, the rated current here at the secondary is 5 ampere. So what is the suitable burden that you should choose from the standard? Should I choose 2.5 or 5 or 7.5, 10 or 15? Or suppose I want to choose a CT based on the IEC standard burdens. So I have to calculate what will be the total volt ampere that the CT will see, the total volt ampere connected at the secondary of the CT. So first of all, I will have to change S of the relay. Now S is the relay, it's 10 volt ampere at 5 ampere. So it is 10 volt ampere, cosine inverse of 0.8. I got this is the volt ampere for the relay itself. So if this is S instead of ZR, I have SR. I'll call this relay SR. Okay, and similarly for the lead, it's just a pure resistance. So the volt ampere is like just I secondary square times the Z of the lead gives me the S of the lead. So that gives me 0.1 times 5 square me. Oh. So this is also on watt because I have just a resistance. All right. And now the total burden, you add these two. I got 12.1 and angle 29. So what does that mean? I'm looking to buy a CT that its burden, maximum burden, should not be lower than, its rated burden shouldn't be lower than 12.1. So if you go to this table now, I go 7.5 low, 10 is low, 15 is suitable. 15 is higher than, okay, 12, so that's 15 is selected suitable burden for this application. Is there any questions? الحين صاحين؟
دكتور
نعم.
الباور فاكتور اللي في الجدول دائما لاقين.
هذه حسب الستاندرد، اوكي، لكن هي طبعا لاقي most of the relays بشكل عام are inductive، اوكي، خصوصا لما نتكلم عن electromechanical. اوكي. بعد اي اسئله ثانيه؟
دكتور الليد وإيش هالمرة ثانية؟
الليد هو الوايرات اللي بنوصل فيها الاوتبوت مال السي تي الكرنت ترانسفورمر باللود مالنا اللي هو يمثل الحين يا الريلي يا الميترنج ديفايس، مثلا الاميتر. اوكي، يعني ريزيستنس مالت الوايرات، وايرات التوصيل اللي هي الليدز.
اوكي شكرا دكتور.
بعد اسئله اخرى؟ So this lead means wire, conductors. So you connect the secondary to the relay. Burden at non-rated currents in some relays. Suppose they tell you the burden is like here in this example. I tell you this relay is 10 volt ampere require 10 volt ampere at 5 ampere, but they tell you now you want to connect it at not 5 ampere, at 1 ampere. So how do you convert this volt ampere from that correspond to 5 ampere to a burden correspond to 1 ampere? That you do it in this way, okay? You know SP, which is the burden in volt ampere, and N represent the nominal. Nominal يعني rated, okay? Rated is the one that's specified by the manufacturer, okay? Now, this nominal burden has to be equal to also nominal. I have to add one thing here. It's also burden nominal, Z burden nominal times S rated nominal. The current, this is the secondary rated current. As I mentioned to you, it is either 5 ampere or 1 ampere as per the two standards. Now, at other than the rated current, so we have to specify the rated burden in volt ampere at the rated current for a given rated burden. Now, if I want to find the same burden in volt ampere at other currents, we know that the related relation between volt ampere and current in this, right? So Z burden times, okay. So this ZB at other burden will not change, okay? Burden not change. So from this relationship, I can find ZB. So ZB is same in both cases, okay? So from which, if we equate both equation for ZB, I can find SAB as SPN times IS over ISN square. So in this case, if IS same as ISN, so the burden is same as the minimal burden. If you choose a current lower than rated current, the burden will be lower than your standard burden, and so forth, okay? This is just an example. It shows you the same thing. Inshallah, in the next lecture, I'm also 9. Now in the next lecture, inshallah, we'll start with going to how do we assess the performance of current transformers? How do you choose them? How do we specify if they are suitable or not? Okay. Now what I consider is just how do we choose the burden of a CT? But I didn't say how do choosing a CT burden doesn't mean that the CT will not saturate during fault. Okay, so this is one condition that I have satisfied today, that we should choose a CT burden suitable to the load that will be connected to. Otherwise, it will be overloaded. Okay. And overloading means overheating of its winding. Okay. So with this summary today, I have covered what's the purpose of CTs and VTs, their CTs polarity marking, CTs characteristics, the definition of an E-point, definitions of a burden, and also different types of CT technologies, the core type and the optical type. And inshallah, next class I will cover other topics related to the current transformers. Do you have any questions? Okay then. So I'll see you inshallah next class. If you have any questions, you just you can ask it at the beginning of the next class. Okay. I'll stop recording.